Hi everybody, welcome back to the Feynman technique. Today we're going to be solving another integral that I got off of Michael Penn's math channel. He got this integral from the MIT 2020 integration bee, I believe. He solved it the traditional way, using integration by parts and the Gaussian integral. I'm, of course, since this is a channel on Feynman integration, I'm going to be using the Leibniz rule for differentiation under the integral sign. Just a quick note, Feynman integration is not necessary for this. You can solve this using traditional techniques along with knowledge of the Gaussian integral. But anyway, let's get started. So the first thing we're going to do is make the substitution u equals x squared. Therefore, du is equal to 2x dx. All right, well, we have the dx part. We don't have the 2x, though. Well, we kind of do. We can make this an x to the fourth times x, and then we can put in a 2 and then multiply it by 1/2. Now we have it. So that would mean I is equal to 1/2 the integral. All right, change of bounds, they won't change. 0 to infinity. We have the 2x dx, so we have our du, and then x to the fourth will become u squared, and e to the negative x to the fourth will become e to the negative u squared. All right, that's looking a little bit better. And from here, you could do some manipulation and do integration by parts, but we're not going to do that. Instead, what we are going to do is create a function of t that's equal to the integral from 0 to infinity of e to the negative tu squared du. Okay, and then we will make the substitution that, let's see, we want tu squared to equal something else squared. We'll call it w squared. All right, so that means that square root of t times u is equal to w. Therefore, let's see, we'll write this as t, no, square root of t, that's fine. Therefore, du is equal to let's see, that's going to be t to the negative 1/2 dw. All right. Okay, so now f of t is equal to the integral from, let's see, that's not going to change our bounds, 0 to infinity, of e to the negative w squared times, let's see, our du will become t to the negative 1/2 dw. So we're going to have dw and then t to the negative 1/2. All right, this part right here, of course, we know this is the square root of pi over 2. So our f of t is both equal to this, and it's also equal to t to the negative 1/2 times the square root of pi over 2. All right.
At that same moment, Ella, uncharacteristically early, hurried into the office from the elevator, her hair still wet. She wore jeans, a t-shirt, sneakers, and
all right, now how's that going to help us? Well, let's take a derivative with respect to t of this expression for f of t and this expression for f of t. All right, so that would give us our f prime of t in integral form would be equal to, let's see, we'll still have the integral from 0 to infinity. We'll still have the e to the negative tu squared du, but now we'll have times the partial with respect to t of negative tu squared. Well, that would just be negative u squared. All right, so there's our f prime of t as an integral. So our f prime of t is also going to be equal to the derivative with respect to t of this thing. Well, that's going to give us, let's see, negative 1/2 times t to the negative 3/2 times the square root of pi over 2. Or we'll just call that negative t to the 3/2 times the square root of pi over 4. Okay. Well, let's take a look at this. If we evaluated our f prime of t at the point 1, and then multiplied it by negative 1/2, we would recover our original integral. So that means that I is equal to negative 1/2 times f prime evaluated at 1. Okay, well, plugging in 1 to this expression for f prime of t wouldn't be useful, but it would be very useful to plug it into this expression. All right, so what would that be? Okay, so let's take this, multiply it by negative 1/2, and then evaluate it where t is equal to 1. All right, so that's going to give us, well, if t is 1, this whole the t doesn't matter. So we're just going to get negative square root of pi over 4 times 1/2, or the square root of pi over 8. All right, guys, there you go. Hope you enjoyed that.